Hey, good morning, everybody. I wish I could be there with you this morning, and I wish I felt good enough to be there. But we're at a crunch time with the final so close that I don't really want us to get behind. So unfortunately, we can't just take a free day here. So I'm going to make a video and finish 5.4, and I'm going to try to keep it as short as possible. And I'll make a second video to do half of 5.5. And so here we go. In 5.3, we talked about something called the Fundamental Theorem of Calculus. And Fundamental Theorem of Calculus there. And it has two parts. The first part that we talked about was really part 2. And part 2 of the Fundamental Theorem, it solves this really important problem, the area under a curve. So you may remember we had definite values, like maybe it goes from 1 to 7, and we got some function, and we're looking from 1 to 7, and that makes an area under that curve. And if we do that integral with the fundamental theorem, that will tell us the numeric area under the curve. Part 1, which is really something I looked at second, it's a little bit more abstract, so I saved it for the last half. It's a little complicated with the idea, but it basically, I'm going to simplify part 1 way down. If you're doing an integral and there's no limits of integration, this one, remember that was a variable? And so the bottom line was that it gave me a function in x, which we had been calling big F of x. And that's where I'm going to simplify it down. So this one we call the definite integral, because we have a definite start and a definite end. This one, it's a variable end, and so what winds up getting the outcome is just a function. So we call this an indefinite integral. And so this is the simplified version right down here of the indefinite integral. It just basically says if you're integrating a function, it equals the antiderivative. That's the answer. So if you integrate a function, you're going to get the antiderivative. Now notice on the integration, there's no limits of integration. That's why it's called indefinite, because it doesn't have a start or an end. It just comes out as a formula. We just get a function answer. And so we talked about that in the last class, and we have a whole table of values that calculate the antiderivatives for us, and we learned all of these back in chapter 2 and 3 when we learned derivatives. All of these are just the derivatives backwards, except when we do the indefinite integral, we're always getting this plus c thing. The definite integral doesn't have the plus c because we're subtracting. So theoretically, I shouldn't probably do this, but theoretically this would be f of b plus c minus f of a plus c. That's the theoretical outcome when we do the fundamental theorem of the indefinite functions. But what happens to the equation is we get f of b plus c minus f of a minus c. And the two c's, because I did two integrals and evaluated at the end limit and the start limit, I get two c numbers, but they subtract each other out, so they're gone. So we don't worry about c on the definite integral. Okay, but the indefinite integrals, yes, we must worry about c. So theoretically, this would be, this simplified version isn't quite the best statement. We should say plus c. Okay, now we started practicing finding these antiderivatives. We did number 1, then we did number 2 in class, and we did number 3 in class. And in every case, none of these, 1, 2, or 3, none of them were antiderivatives. They didn't have nice answers. So in all 3 of these cases, if you look back at your notes, you can see a pattern. We used algebra or trig to reorganize the problem so that we could change it into some of these simple antiderivatives. So this is what we're always hoping to find, and if we don't have it, then we're going to have to use algebra or trig to simplify. All right. Now, that is all indefinite integrals, 1, 2, and 3. Number 4, it is not an indefinite integral. It has specific limits. So this one we're doing a definite integral, and it's always good to practice. And I wanted to put this one in there just so you can kind of see what's going on here. So let's see if we can break this down. This is going to equal. Now, I'm going to write a lot of steps, which once you start getting used to this, you can skip these steps. But it's a subtraction. So that means I can integrate from 1 to 2 of x over 2 dx. Don't forget the dx. Minus, do another integral from 1 to 2 of 2 over x. And don't forget the dx. That's the differential. It's very critical in the integration. And then we can just use the laws and the properties to try to find an integral that we can do. Now, the first piece has x in it. Hey, that looks like this one here. It looks like a power function, x to the 1 power. It also has a coefficient multiplying it, a c number. In this case, the number is a 2. So you could skip this step and maybe do that integral in your head. But at first, maybe that's not the best plan for you. So I'm going to take and factor out the 1/2 coefficient, 1 to 2, integrate x dx. Now that, I've changed it into something very simple. Minus, I'm going to factor out the 2 in front and integrate that one from, that's 1 over x dx. Also a very simple integral. So this will equal, I have this coefficient 1/2. And then I have to do the integral, which is 1/2 x squared. Minus, now I have this coefficient out front too, and I have to do this integral. The integral of 1 over x is the natural log of x. Now I'm going to evaluate this, and we put this bar or this bracket here to say we're going to evaluate between 1 and 2. So essentially what I'm saying here is we have to do f of b, plug in 2, well, let's just say 2, f of 2 minus f of 1. That's the fundamental theorem of calculus. So all I have to do is plug that stuff in. So if I plug in, I'm going to have 2 squared, which is 4, and this half times this half makes 1/2. I'm sorry, 1/4 times 4 minus, now I have to do, I should probably color code this. I'm going to do that. So f of 1. Okay, so I plugged in the 2 into the x squared, and I'm going to plug the 2 into the natural log, which is just -2 times the natural log of 2. Now what I've accomplished so far is the first half of the fundamental theorem. Now I need to go minus. Now I got to plug in the 1 and evaluate again. Now because of the minus, you're going to need parentheses here because that minus will distribute. So I plug in 1. 1 squared is 1. 1/4 times 1. And then I'm going to plug in natural log of 1. That's -2 ln of 1. Now it turns out if you simplify some of this, the natural log of 1 is 0. And so we really only have a subtraction distributing to the 1/4, and this would be our final answer. 1/4 times 4 equals 1 minus 2 ln of 2 minus 1/4, and I've got 2 constants in there, so I can minus the 4th from the 1, and I'll get 3/4 equals, nope, not equals, 3/4 minus 2 natural log of 2. There's my exact value. And this would be the area under a curve. Now it's an unusual curve, but there we found it. All right. You can pause and kind of work through the steps, maybe rewind and try to do it by yourself without looking. That would be a good study strategy. But let's go on to the next page. So we're finished practicing the fundamental theorem, and we're going to use the fundamental theorem now to give us some applications. And one of the applications of the integral is something called the net change theorem. If you are integrating speed, rate of change, then the integral of speed is position. So we did this a long time ago with derivatives. But if we integrate acceleration with respect to time, we're going to get velocity. If we integrate velocity with respect to time, we're going to get position. And that's what they mean by, sometimes they'll use the word displacement, absolute distance. So I encourage you to read up in the online textbook. Read up on pages 406 to 407. It'll help you get used to some of the vocabulary around the integral, so you can kind of get more comfortable with what we're doing. Okay, now let's do this example number 5. We got a little function sketched on the side, and in 5.1, if we would have done rectangles, we would have had rectangles in here, and we would get an approximate area that was positive. And if we did this section, we'd have an approximate area that would be a positive number. But when we flip things upside down and do our rectangles, we're doing rectangles that have height, I'm going to put quotes around the height, times delta x, the width. And the height is a negative number. So each of these rectangles is going to be a negative times a positive. So this is a negative area. Okay, now that's weird to say, and I'm just being loose with the language, but when we add up the positive area and the negative area and the positive area, so we'll have a positive area, a negative area, and a positive area. When we add that all up, there's going to be a net change. So it looks like it'll be a negative answer because the blue above is a little less than the red below, but we don't know. We'll see how it goes. Okay, so that's what we mean by net change. When you integrate a function under the curve and part of it is below the curve, that part is going to negative out the positive parts. Okay, so let's practice. We've got an integral here, and I'm going to go a little faster here. We need the fundamental theorem. So basically this means we've got to get the antiderivative at 2 minus the antiderivative at 0. And so we're going to integrate each of the terms. Now there's 3 of them here. Now I'm not going to write out all the steps this time because this is my integration. I want to integrate x cubed. Now the coefficient is just multiplying the answer to the integral. So the integral of x cubed is going to be add 1 to the power, it goes from 3 to 4. So I'm going to have x to the 4th, and it's times 1 over 4. Now, I like writing it this way better, less writing. But there's the integral of x cubed. The second term is just x. The minus 6 is a coefficient multiplying my integral, so I'm going to integrate x. And the integral of x is x's first power, add 1, we're going to get x squared, and we're going to divide by that power of 2. And the last one, wait, that looks a little weird. It too has a coefficient, minus 3, and then we're going to integrate this thing that's left over. I don't recognize that. And I'm hoping, wow, how am I going to integrate that thing? Well, I'm hoping there's a formula for it. Is there an antiderivative of this? I'm going to go back to the derivative, the integrals, and I'm looking right here. 1 over x squared plus 1. There it is. It's a tangent inverse result. So the antiderivative here is tangent inverse. Okay, so the integral of that piece, I'm going to erase it and just put what it is. It's tangent inverse. Tan inverse of x. And now we're going to integrate from 0 to 2. So I have to find f of 2. So that's going to give me, I've got to plug the 2 into all three of these terms. Okay. There is a lot of simplification, though, that I should do. I think first, because the 2 and the 4 cancel, I get x to the 4th over 2. I can reduce. The next one, I get 6x over 2, which is 3x squared. And on the last one, I can't do anything with that one as far as simplifying. And I'm integrating from 0 to 2. And I'll do f of 2 in blue. So when I plug in 2, I'm going to have 2 to the 4th power, which is 16 divided by 2 is 8. When I plug in 2, 2 squared is 4, times 3 is 12. And when I plug in 2 into the tan inverse, nothing really nice simplifies there. Okay, this is my f of b part of the fundamental theorem. Now I have to minus. Now, especially the second term, you have a subtraction here. This subtraction isn't only on one thing, it's on the whole. So you're always going to need parentheses on that whole group. So now I'm going to put f of a. So that means 0. Maybe I should just put in 0. And that means putting 2 back in here. So that was the fundamental theorem with 2 in it. So on the second part of the fundamental theorem, I'm going to plug in 0. Okay. Plug in 0 here, that's 0 squared, 0 to the 4th power. Plug in 0 here, minus 0. Plug in 0 for tan inverse of 0. Now, if you're not familiar with tan inverse too much, you may have to use your calculator for that guy, but that turns out to be 0 as well. So when we simplify, we get a final answer here. It equals negative 4 plus 3 tan inverse of 2. And if for some reason we needed to know the specific area under the curve, it's not quite truly an area, but it's a net change. It's approximately negative 0.67855. So the positives and the negatives kind of balanced each other out. There was a lot of canceling of positive area with negative area, and there was a tiny bit of negative area left over. So it's mostly, the graph is mostly below the curve. Okay, pause that one, go back, kind of study it out, write it down, and maybe try doing it on your own without looking. But let's go to the next example. So back in the old days when I first started teaching calculus, we spent a lot of time on a topic called rectilinear motion, which is basically two-dimensional. No, one-dimensional, I mean. Imagine a particle is moving, and here's your time axis, and time is here, and you start the particle begins to move. Now, it's moving with the velocity, so if velocity is positive, it's going to move forward. If velocity is negative, it's going to move backwards. So it's just going on a one-dimensional line. And if we actually start it at time equals 0, the velocity will be negative 6. So that means the particle has to be moving backwards at first. And then when t gets big enough, the velocity may change to positive. It will change to be positive. And so the velocity will start out moving at negative 6 meters per second. And then it goes slower and slower and slower, and the velocity goes down to 0. And it stops moving. And then the next instant, the velocity changes to positive, so then the particle would be moving back the other way. Now, what I'd like you to see is there is a net change here, because part of the time I have velocity equals a negative number. And then part of the time, I have velocity equaling a positive number. And so there is a net change in this problem. So when we do the net change, we're wondering, I'm going to make this a little bit shorter. They're going to cancel out. Some of the positive will cancel out some of the negative, and there's going to be something left over. Now, so notice the word velocity. There's velocity. That's the rate of change. And this is the vocabulary I was telling you about when I mentioned earlier about position. Another way to think about position is displacement. It's going to be similar to this guy, how I had some positive and some negative. And with the positive and negative, there's a canceling out. Same's going to happen here. With positive and negative, there's going to be some canceling out. Now, I didn't really detail out the picture very well. So, but I wanted to give you the idea of finding the displacement. So let's see. Let's start by integrating the velocity. So if we integrate the velocity from 1 to 4, the velocity with respect to t dt, that's going to be equal to the displacement. So it's going to equal the position function from 1 to 4. So all we need to do is the antiderivative, and that will tell us the position of the object. So we're integrating 1 to 4 of t squared minus t minus 6 dt. Don't forget the differentials, the dt's or dx's. And now we're going to integrate that. So the integral of t squared is 1/3 t cubed. Minus the integral of t is t squared over 2. And the integral of 6 is minus 6t. We're going to evaluate that from 1 to 4. So that's just the same thing we've been doing. It's f of 4 minus f of 1, where big F is the antiderivative, which we got. We got the antiderivative. So now I'm just going to plug in numbers. And when I plug in 4, I'm going to have 4 cubed, which is 64 over 3, minus 4 squared is 16 divided by 2 is minus 8. And 4 times 6 is minus 24. That is the f of b part. I'm not done. Now I need to do the other one. Now I'm subtracting. Don't lose that subtraction. It goes on the entire result. Subtract the entire result of this f of 1. I'm going to plug in 1. 1 cubed is 1 over 3. 1 squared is minus half over 2. No, it's just 1 over 2. And plug in 1 to 6t and I get 6. Oops, minus 6. Okay, now, if you're not great with fractions, put it in your calculator. You can type this. There's in the math button, there's a thing that looks like this. It says convert to fraction. So you can type that entire expression as long as you include the parentheses, and it will give you the fraction value. So I recommend you learn that because it'll save you a lot, and that way you won't get mistakes just because of fraction math. But in the end, it turns out when we add and subtract all those fractions together, we get negative 9/2 meters. Okay. So what happened? Well, we didn't start at 0 seconds. We started at 1 second. So the particle has already been going backwards. Here's time. And so now the position of the particle at with my real start of 1. Trying to get that off. Okay, had a little glitch in the tablet that I'm writing on. Now I got it fixed, so I'm back. I want to help you with some intuition here. What are we talking about? This displacement. What's going on here? Okay, so initially when I drew a picture, I started at 0 time, but we're not beginning at 0 time. We're beginning at time equals 1 second. And you can actually put 1 second up into the velocity equation. 1 squared minus 1 is 0. Oh yeah, wow, that's 0 minus 6. It's still, the velocity of this particle is got a negative velocity, which means it's moving backwards. So if I were to plot the position with time, my particle is actually moving backwards. Now, eventually the time is going to go to 0, which means the velocity is slowing down. And then the particle is going to turn at a 0 velocity. It'll change direction and have a positive velocity after that. And so the particle is actually going to turn, and then it's going to go positive. So what we mean by the net change here is that most of the particle's time was spent moving backwards. So that would be all negative. And a little bit of that particle's time was positive, moving forward, and it didn't quite get back to where it started. So the displacement is this part right here, which is the net displacement. When you subtract out all the positive and negative, it started at a point and it wound up back 9/2 of a meter. So we're still kind of in the negative territory of that position. All right, so I wanted to give you some intuition here about this guy. Now, I'm going to erase some of this to make room for the next question. That was part A. Now we need to do part B. Part B is a little more involved. Okay, the second question is about not distance. I'm sorry, I said it wrong. The first question was about displacement. The second question is about distance. Okay, now distance is always positive. I never say it's negative 150 miles to LA. I never say that. It's just not normal talking. We say, oh, LA is 150 miles away. It's a positive value. Technically, when we think of distance mathematically, we're thinking of the absolute value. So I have a distance here that might be an absolute value of a negative displacement. Let's say it's -6. And I'm going to take the absolute value of that distance. This is just hypothetical here. And then I have this positive distance, which is the absolute value of, let's see, that's 9/2. It's 4.5. So 4.5, 1.5. Now, on this part, the absolute value is 1.5. That part, the absolute value of that is 6. So that will give me a distance traveled. So it's a total distance. How far did I go back? How far did I go forward? And add up everything. This is not a net change when we talk about distance. So this problem gets a little bit more challenging. So how are we going to handle this? We're going to have to take the absolute value of the velocity. So now we're going to integrate from 1 to 4 of t squared. Oh, let me write it formally first. The absolute value of the velocity, dt, which equals the integral from 1 to 4 of, no, let's wait for a second. Now, here's a dilemma. Because the absolute value of the velocity function is sometimes negative. It's the red part. So what we need to do is integrate the absolute value of velocity on the red part. Now, the velocity is negative. So we need to make it opposite to get the distance. So we would be integrating a negative of the velocity. And that would give me a positive red number. Plus, I need to integrate the velocity on the blue part of the graph. But the blue part of the graph, the velocity is positive. So if I'm doing the absolute value of a positive, it's just the integral of the velocity. So that's supposed to be a v there. So part of this, because the absolute value is part negative, I have to make the negative part into a positive. And I do that by switching the sign there. Now, I need to know where that velocity changes direction. So how do we do that? We got to find the time when that change takes place. So we're going to have to do some velocity sign analysis. We're going to have to analyze that velocity equation and find out when the velocity is negative, when is the velocity 0, and when is the velocity positive. Now, we know how to do that because that was a big part of chapter 4, was looking at sign analysis. So I'm going to take the velocity equation and see if I can figure out when does it equal 0, because that would be a critical number. And it's factorable, t. We're going to have minus 3 and t plus 2. And time, when does that equal 0? So time equals negative 2 doesn't really make sense. Plus, it's also not in our domain. But the other equation, t minus 3, could equal 0 when t equals 3. That's a critical number inside this time interval. Something happens. The velocity went to a 0. So right here, at this point, where I'm at 3 seconds into it, something happened. It went from a positive to a negative. Now we can do this a little bit further and look at a sign chart here. Let's look at velocity and find the velocity signs. We have t plus 2, t minus 3, and we have a time axis here, and something critical happens at negative 2. Velocity is 0. And something happens at 3. Velocity is 0. And what is going on with the signs of the velocity on the intervals before those regions? I can look at t plus 2 and plug in a number before negative 2, and it's negative. And I can look at t minus 3 and plug in a number before negative 2, and that's also negative. So the velocity right here is positive. I can plug in a number between negative 2 and 3, like 1. T plus 2 equals 1, that's positive. 1 minus 3 is negative. So the velocity is negative in this region here. So it's going backwards. And then after 3, so at 3, the velocity is 0. So I've got 0 velocity and 0 velocity. After 3, I can plug in a number like 5. Well, no, it doesn't go up to 5. Let's plug in 4. That's positive. Plug in 4. That's positive. So after 3, the velocity switched to a positive. Now it's going forward. Now, we're not really looking at this section of the graph because our time isn't negative. In fact, our time starts at 1. But at 1, it's negative. So from 1 to 3, the particle was going backwards, has a negative displacement. And then after 3, it turned around. And it made a change of direction and went back the other way. This all happened right there at 3 seconds. Okay, now, if we're going to integrate this, we have to realize that this velocity is negative and it won't give us the distance. It'll give us a negative number. And this distance is positive. That is the distance, so we need that one. So what we have to do to accommodate this problem is we're going to have to integrate from 1 to 3 on the velocity. And when we do that, instead of having a negative number, we're going to change it to its opposite. So it will come out as a positive. This way we get a positive distance for that red section. Plus, we're going to integrate the rest of it from 3 to 4 v of t. Now on this part of the velocity and position function, the particle is moving forward, so the position will have a positive distance, so we don't need the absolute values, we just integrate that positive number. All right, so this is the fundamental theorem, but we have to do two different integrals. And we have to culminate these two integrals here. So the red one will equal, we actually have the integration already done, except I'm changing the sign on the red one. So instead of t cubed over 3, I have negative t cubed. Negative t cubed over 3 plus, same sign change, t squared over 2 minus 6t, sign change. So the integration on that red section comes out negative if I don't adjust it. And so I want the distance, I need the absolute value, I need to change it to its opposite, and we're going to integrate from 1 to 3. Then we're going to add another integral. This time we're integrating the integral, the v, from 3 to 4. Now that doesn't have a sign change, so I'm going to have t cubed over 3 minus t squared over 2 minus 6t, and I'm going to evaluate that one from 3 to 4. Now the rest is just plug in. It's plug-in math. You should practice this. I'm not going to detail it out. Wanted to keep the video kind of short, but this comes out to be a positive. When you do f of 3 minus f of 1, you get a positive distance of 22 over 3. And you should try that and see if you can get that. When we do the blue one, and we do f of 4 minus f of 3, that one comes out to be 17 over 6. And so we get a total distance of 61/6, which is about approximately 10.17 meters. There we go. That one's a little weird. I think you have one of these in your web assign, and it's more of a challenging one because of this analysis that we had to do to split the integration into the negative part and the positive part. Anyways, good luck with this. So really apply yourself, learn lots, study hard, and I hope to see you back in class on Tuesday. Oh, by the way, look for the 5.5 part 1 video. That's going to come up a little bit later.